Okay, I have found the perfect display for my shifter knob project. It's round, it's small enough to fit inside a 3D printed shifter knob, and it's very cheap. The price is slightly below $4. And as you can see, it can also display colors. So today I will show you how to use that display together with the Arduino UNO. But first I need to tell you 3 things. First of all, please write a comment and let me know what car do you drive. I would like to create a few different versions with different logos, and it will be nice to know what are the usual brands out there. The second thing is, this video is actually a part of the custom shifter knob series, and I believe that this is the video number 7. In the first video, I have used Hall sensors to determine the current gear based on the shifter lever position. In the second video, I was experimenting with this 7x11 LED matrix display. The third video was about 3D printing a custom shifter knob to put that display inside. Video number 4 was about a different display, the 5x5 RGB LED matrix display. Video number 5 was about using this shifter knob with the PC game using SimUp application. And video number 6 was about the hexagonal NeoPixel display. And here we are on the video number 7. Now you don't need to watch all the previous videos, but if you have any questions, it's possible that the answer might be there, so in any case, I'll put all the links to those previous videos in the description. The first thing that I want to talk about is the sponsor of today's video, which is PCBWay. You can use their services to get pretty much everything that you might need for your project, including PCBs, PCB assembly stencils, but even things like 3D printing, CNC machining or injection molding. Actually, there is much more, so anything you need, you might find there. And if you need PCBs and you use the link down in the description, you can get 10 PCBs for free, only paying for shipping. So thank you PCBWay, and let's finally get to our display. Again, this is the round display, but it's not 100% round, and what I mean by that is if you tilt it, you can see that the bottom of the display is actually cut off, so we need to keep that in mind. This is the IPS display, which means it has a nice viewing angles and nice colors. The brightness is decent, it's not something that you will use outdoors, but it should be fine inside a car. The thing that I like about this display the most is that you can get it in a few different versions, and one of the versions is this one with a glass lens on the top of the display, and I think that it just looks perfect. I mean, I don't know how visible it is on the camera, but it's not flat, it's slightly round, and I think that it will look great when you place it inside a 3D printed shifter knob because it will kind of mimic the shape of the knob. I mean, especially if you compare it with the version without the lens, the difference is quite huge. This display has a chip, it's the ST7789H2 that uses the SPI connection. The cable is included, it has 8 wires, so we will need 8 pins, but you can see that it has female hairpins, and I want to use that together with the Arduino UNO that also has female hairpins, which means that I either need to use some kind of shield like this one from the F-Robot that has male hairpins, or I need to place some male hairpins in between those female hairpins. But we need to first know the connections. And the second thing that I like about this display is documentation. There is this wiki page with all the details, and you can download all the schematics, all the datasheets, as well as the sample code. So let's actually do that. And if I open the downloaded zip file, we have demos for the Arduino, ESP32, and so on and so on. And if I open the Arduino folder, we have demos for the Arduino Mega and Arduino UNO for both the hardware SPI and software SPI connection. There is even this picture folder where there are photos of this demo running on the Arduino, so we can see what we might expect. And I guess we can open some of those images and see the connections, but we can as well locate this PDF file that has all the connections on the page number 2 and 3. And if I zoom in a little bit, you can see that we should connect the ground to ground, the VCC to 5 volts, the SCL, the serial clock to pin number 13, and this is quite important because this is the hardware SPI clock on the Arduino UNO, then the SDA, the data pin to pin number 11, again this is the hardware SPI data pin on the Arduino UNO, and then we have pins reset, the data command, the chip select and the backlight, and those are connected to pins A4, A3, A2 and A0. I guess we can connect those to any pins, but I will use those listed pins at least for now. So let's use the provided cables to connect the display to the Arduino UNO. Also the colors are slightly confusing because the VCC is in a black color while the ground is red color. Usually it's the other way around. So once the display is connected, we can jump back to the downloaded zip file. And in here I will open the Arduino UNO demo hardware SPI folder and open the 01 simple test and open the INO file. And the sketch looks like this. You can see that we are using no libraries except for the SPI, which should be already included in the Arduino. And just in case, the connection is listed in here one more time. So I think that at this point, we can just select the Arduino UNO board and hit the upload button. And when the sketch is running, it first shows some full screen background colors. Then it also shows some filled circles. And then also some outline circles. And then it continues again from the beginning. So we know that the display works. Let's also try some other sketches. Inside the downloaded folder, we have a few more. I will open the second one, which is called the clear screen. So again, open the UNO file. And here we can see that we need two more libraries, being the LCDWiki GUI and the LCDWiki SPI. And both of those libraries were included in the downloaded folder. If I go to Libraries folder, there are two zip files for those libraries. And we need to install those by going to Sketch, Include Library, and clicking the Add Zip Library and selecting those zip files. I've already done this, so all that's left to do is to select the Arduino UNO board and hit the upload button again. This sketch is actually simpler even than the first one. It's just clearing the screen with different colors. But I think that it nicely shows what could be the maximum speed that we can get from the Arduino UNO. You can see that as the screen updates, it takes about, 1 or maybe 2 seconds to update the entire screen, and we cannot get any faster than that. So if you want to update the whole screen, that might be an issue because it will be quite slow, but thankfully we will be only updating a small portion of the screen. But before we do so, let's quickly go through all the other examples. The next one is called Colligate Test, not quite sure what that means, but it uses the same libraries and there is quite a lot of stuff going on, so let's upload it to the Arduino as well. And it looks like it's some kind of performance test. It draws as much stuff as possible and then it measures how much time it took to draw that stuff. But even without looking at those numbers, I think it's quite obvious that the Arduino UNO is quite slow. Anyway, let's move to the next example. This one is called the display graph and it's actually not for drawing graphs but for graphics, so let's upload this one as well. And we see all the different shapes and colors. I quite like this demo, it shows quite a lot of different things, but I think that it's time to move to our project, so let's just try one more example. And I will try the last one, which is called the display clock, and it should hopefully display the analog clock, so let's upload this one as well. And indeed we see the animated analog clock. And in here the performance is not an issue because it only needs to update once every second, and I think it's not updating the whole screen, only those hands. So we've seen quite a lot of different examples. Let's see if we can use any of the code to draw our custom gear indicator. I will start with the very first example called the symbol test that doesn't use any libraries, and I will go all the way down to find the setup function, so the setup function is down there. And as you can see, it first initializes the SPI connection and then sets the pin mode, and then it calls the LCD initialization, the LCD init function. If I control click on this function, it will jump to that function, and in here there is some initialization sequence for the chip to make sure that the display works properly. We don't need to mess with that code, so I'll jump back to the setup function. I think that was all that was there, so that's correct. And then inside the main loop, we are clearing the display and then drawing the circles and drawing some other circles, I guess. And actually the LCD clear function is quite important, so I'll control click on this one and jump to that function. And this function clears the display with certain color defined with this J variable. And it does that by going over every single pixel on the display. So the display resolution is 240 by 198 pixels. And for every of those pixels, it sends 2 bytes of data. And that's because every single pixel, every single color is represented by 2 bytes. And since 1 byte is 8 bits, 2 bytes mean 16 bits. And that's the color format being used, the 16-bit RGB, also known as the RGB 565, because 5 bits are being used for the red channel, 6 bits are being used for the green channel, and 5 bits are used for the blue channel. And 5 bits are 32, 6 bits are 64, and 5 bits are 32. So if you multiply those three together, we get 65536 colors. So let's see if we can fill the display with our own color, and I found this RGB 565 color picker. So let's just pick some random color, I don't know, for example this blue one, and then I will copy this value for our color and use it in our code. So inside the loop function, I will pretty much comment out everything that's in there and only keep the LCD clear function with our color. So this should be the blue color. Let's try to upload it to the Arduino. And indeed, the display is now filled with the blue color. Of course, we don't have to use the same color for every single pixel. We can do something else and, for example, first send the value of the variable I and then send the value of the variable M, which are for those loops. And if I upload it again, we get some kind of rainbow image. We can also draw some completely random colors simply by using the random functions. So I will send the random value between 0 and 255. And of course, I need to do that 2 times. And if I upload it now, the display is slowly filling with random pixels. Also, the filling of the screen is much slower now because the random function takes some CPU cycles on the Arduino UNO, and as a result, it takes a few seconds to update the screen. So we know how to draw pixels, how to draw random pixels, but what about the drawing an actual image? And we will again update the pixels on the screen, but we need to first store the image somehow. And actually, before storing the image, we need to draw the image. Let's open Photopea, which is a free online graphic editor similar to Photoshop, and create a new image in some small size, for example only 32 by 24 pixels. And I want to fill this image with some random stuff so I can see that it works. So I will just do whatever I want. For example, I will select the selection and fill this selection with some gradient, for example going from black to white, like so, and maybe another gradient with the rainbow colors, so a new selection, and again the gradient going over all the rainbow colors. Then I will maybe select the pencil tool and draw some pixel patterns, so maybe something like this. I want to basically draw as much stuff as possible, just to make sure that everything works as expected. And maybe I can even add some text and saying hello world, or at least the hello message. So let's make it smaller, like that. And I guess something like this should work as the test image. Now I need to export it, and I usually export it as the PNG image, but I already know that the software that I will be using doesn't support PNG images, so I'll export it as the bitmap image, so BMP image instead, and name it properly, for example test image. Hit the save button. And now we need to convert this image into the C-style array. If I go back to the downloads folder, there is this folder number 7 that has this tools image to LCD application, and if I run it, if I open it, it looks like this. And this is specifically made for converting images into the C-style arrays. There is also the image in the downloads folder that's showing what settings should be used. So if I show it like this, I can see that the first thing should be C-style array, which is correct. The next setting is just hard to tell from the Chinese, but if I change this to the vertical scan, you can see that this image changes, which makes me think that it should be set to horizontal scan. The bits per pixel should be 16 bits, but it's kind of confusing because the 16-bit is here twice, but I guess the second 16-bit is actually 18-bit, so it will be the first 16-bit. And then the size of our image is 32 by 24 pixels. So I just need to open the image. And one thing that I found compared to this image is that you want to check the MSB first, the most significant bit first. Otherwise it was not drawing correctly. So with all the settings set, we can jump to the 16-bit color preview to see how it looks like. And then we can click the save button to save it as a C file. And once you do that, the file will automatically open in a notepad. And that's great because we want to use that code inside our sketch. So just copy this into the clipboard, jump to our sketch and just paste it somewhere. For example, in here, and let's just put the LCD clear function into the initial state where it was just filling the screen with some defined color, like so. And then I will copy this function and paste it one more time, and let's just rename it to draw test image instead. Now for now, I don't need any parameters, but I need to take a closer look at what's going on inside this function. So we already know that we are sending 2 bytes of data for each individual pixel, but before we actually do that, we are calling this address set function, and I guess this is setting the area where the pixels will be filled. So for now, it's setting the area for the entire screen, but let's maybe change that and draw the image somewhere in the middle. So for example, X and Y position will be 100, and then the right edge will be 100 plus the width of our image, which is 32, and the bottom edge will be 100 plus the height of our image, which is 24 pixels. However, by testing this, I found out that this has to be 1 pixel smaller, so -1 for both the right edge and the bottom edge. And then again we go over every single pixel and we send 2 bytes of data. I think that what I can do instead is to have only one for loop, like so. That will go over every single byte inside our array, which is named the GImageTestImage. Let me just copy the name in here. So it should go over the width of the image, 32 pixels, times the height of the image, times 2 bytes per pixel. And if I do the math, so 32 times 24 times 2, it's 1536, which is the number of bytes inside our array, so it's matching nicely. And for every single byte, I will just send the data, and the data will be the GImageTestImage of the index I. And I think that's all that we need to draw our image. So inside the loop function, I will first clear the display with the blue color, and then I will draw the image like so, and maybe wait a little bit. So let's just put some delay, for example 10 seconds, and we can try uploading this to the Arduino. And sure enough, after a few seconds, we see the very tiny image in the middle of the display. Let me actually try to zoom in as much as I can, but it looks like that it's matching our original image one by one. That's also because I already knew that you have to click the MSB first checkbox in the image to LCD converter utility, and that you have to set the addresses inside the Arduino code 1 pixel smaller. Now this image is nice, but it's very tiny, so what if we want to draw much bigger image or maybe more images? And that will be a problem because if I jump back to our sketch, you can see that we are using 75% of the dynamic memory of the RAM memory because there is only 2 kilobytes. And with our image being sized 32 by 24 pixels, requiring 2 bytes for each individual pixel, we are already using 1.5 kilobytes of the 2 kilobytes of RAM memory. Thankfully, there is also a flash memory, and that's slightly bigger, being 32 kilobytes, which will allow for storing bigger images, but we have to first tell the Arduino to keep the data in the flash memory and not copy it to the RAM memory on the startup. And we do it by using the word progmem, so if I just type in progmem, that will tell the Arduino to keep the data in the program memory in the flash memory. However, once we do that, we have to use a special function to read the data back in. And if I open the Arduino documentation for the progmem, the function should be there, and it's called the program read byte near. So I'll just copy this function into the clipboard and paste it in our code. So we want to use the LCD write data function, but we will get the data using this program read byte near function of our gimage test image. And we don't actually reference this as an array, but this is the starting address of this array plus the index I. And that should be hopefully enough to draw the image from the program memory, so let's just upload it to the Arduino. And if everything goes right, there should be no visual difference. We should see the very same image on the display in the middle of the display. But if I go back to our sketch and show this sketch and the previous sketch side by side, you can see that previously we were using 75% of the RAM memory of the dynamic memory, and now we are using almost none. So this way, using the program memory, we have about 32 kilobytes for our images. Let's update the function to not draw just this one particular image, but any kind of image. And for that, I will just copy this function and call this function simply draw image. And we need to know a few parameters. We need to know the X position, and I'm using the byte variable because it one goes between 0 and 255. And since the width and the height of our image is smaller than 255, that should be enough to hold all the values. Then we of course need to know the Y position. We need to know the width of our image and the height of our image. And then we of course need to know the individual bytes of our image. So we'll just call this image data, and this will be the array of bytes. So inside our function, let's delete the stuff that we are not using. And maybe instead of defining those I and M variables, let's just define this inside the loop. So we first set the address to be X position and Y position. And the right edge will be X position plus the width of our image minus 1. And the bottom edge will be the Y position plus the height of our image minus 1 pixel. Then we will go over every single byte. And that means going over the width of our image times the height of our image times 2, because we need 2 bytes for every single pixel. And then we will send the data using the LCD write data, using the program read byte near function to read it from the program memory. And we will send the image data, so image data plus I. And I think that this should be enough to draw any custom image. So let's test this function, and I will test it with the very same image that we already have. So inside our loop, I will remove the draw test image and the delay, and I will call this draw image function. And just to see something different, let's draw this image on the random position. So the X position will be random, going from 0 to 240 minus the width of the image. And the Y position will be the random function, going from 0 to 198, which is the height of the screen, minus the height of the image, which is 24. The width of the image is 32, height of the image is 24, and the name of the image is up here. It's this one, the gimage test image, 32 times 24 pixels. And maybe what I will do as well is to move this LCD clear function into the setup function. So first we will just clear the screen with the blue color, and then inside the loop we will be drawing those images as fast as possible on random positions. Let's upload this to the Arduino UNO and see what happens. And as expected, the screen is first filled with the blue color, and then we draw the image on random positions. And surprisingly, it looks quite fast. When I was using this display, this test actually gave me a confidence that I can use it for our gear display indicator because I should be able to update just one particular digit with a different color fast enough. So I think at this point, it's time to create that custom gear indicator image. I will keep using Photopea, but this time I will create an image in the full screen resolution, being 240 by 198 pixels, which is about this size. But if I look at the actual display, it looks something like this. So imagine this is the circle, so this area is actually not present on the display, but if we want to align something to the middle, to the center of the screen, we cannot align it to the center of the canvas, but we need to align it to the center of this circle, and we of course need to keep in mind that anything inside those areas will not be visible. So I think that it would make sense to create this helper circle. I will open those shapes and select the ellipse tool, and in the size drop-down menu, I will select the fixed size to be 240 by 240 pixels. And then position the circle like this to be aligned on the top side and the left side. This is optional, but I might add a new color fill layer in the dark gray color so the white is not that much shining into my eyes. And then I will select the rectangle tool and draw a new rectangle in the size about, 160 by 4 pixels, like so. And of course I need to double click this layer and change the color to be white. And then I will select the layer together with the circle using the shift key and align it to the middle for both the vertical and the horizontal direction. So this will be the middle line of our edge shifter pattern. And then I will draw another line using the rectangle tool about, 4 by 70 pixels. Align it to the left side of the other line using the arrow keys on the keyboard. And then I will create a copy by pressing the Alt key on the keyboard and dragging it to the right side 3 more times, like so. And then I will select all 4 layers, center it vertically, and then click this button to have equal gaps. And then maybe I will select also this layer and the circle, and again center it vertically to have everything aligned to the center of the display. Now for the leftmost line, I only need the top half of the line, so I'll zoom in a little bit, and then go to Edit, Transform, Scale. And by default, if I drag it around, you can see that it's scaling for both the width and the height. So what I need to do instead is to again select Transform Scale and press the Shift button on the keyboard to only scale it for the height, like so. Press the Enter key, and we have our edge shifter pattern finished. Of course, I want to add the labels, the digits, and for that I will select the Type tool and just type the R for reverse, and I can use any font I want, but I've decided to make this BMW themed, and for that I've downloaded actually a custom font called this BMW Helvetica, so download this font, and then go back to Photopea, open this font drop-down menu, and click this Load Font button. Select the downloaded zip file and click the Open button, and it will add this font to our drop-down menu list, so I will type in search for BMW, and select this BMW Helvetica font, maybe make it slightly bigger, for example like 36 pixels, make it center aligned, if it's not white then make it of course white, and then position it to the correct position, for example something like this. Create a copy, which could be done in many different ways, for example right clicking the layer and selecting duplicate the layer, double click the layer icon and type in digit number 1, or I can as well create a copy by Alt and Shift clicking on the keyboard and dragging the layer around. And this will be the gear number 3, this will be the gear number 5, and so on and so on. And in the end, after tweaking the positions with the arrow keys on the keyboard, it might look something like this. As for the positions and sizing, this is the edge of the display, but it probably makes sense to leave a little bit of space in between those digits and the edge of the display. Now this image looks nice, but it's kind of boring. We are using the color display, so it might make sense to show some colors and maybe show some logo. And again, I've decided to make this BMW themed. So I searched for the BMW M logo and found this one on the Wikipedia. I will open the source file, which is this one, and copy the URL into the clipboard, and then go back to Photopea. And in here I will select File, Open More, Open From URL, and paste this URL. And I want to place this into the current project, so hit the OK button, and we have our logo in here. I will make it slightly smaller. For example, something like this. Hit the Enter key on the keyboard, and then again select the logo and the circle. And I might as well close this tab because I don't want to see it. I want to have more space for the layers pane. And then align this logo with the circle by clicking this Center horizontally and Center vertically button. To have some space between the logo and the lines, I will double click the layer to open the layer style and then add the stroke effect. I will change the size to be only around 4 pixels, and then of course change the color to be black color like so. and now there is a clear separation between the logo and the lines. And I think that the image like this could be the final design, and I would like to of course see it before I start splitting this into smaller images. However, when I get the size of the image, 240 pixels times 198 pixels times 2 bytes per pixel, I would need about 95 kilobytes, but I only have 32 kilobytes on the Arduino UNO. But I think that I should be still able to display this image, and the idea is that I will just send the data from the PC to the Arduino UNO, and then the Arduino UNO will send the data to the display. And just because the display has enough memory to hold the entire image of the entire screen to have the frame buffer for the display, I think that something like this should work. So let's keep the Photopea application opened and jump into the Arduino IDE. In here we are still drawing the image on random positions, but instead of drawing the image, I want to draw whatever data we get from the PC using the serial communication. And for that we need to first establish the serial communication using the serial begin function, so just copy the serial begin function into our code and paste it inside the setup function. And the most important thing is the speed. I want to send the data as fast as possible, and if I open the serial monitor, we have quite a lot of speeds to choose from. I did find out that this 115 200 bauds works nicely, so I'll use the same speed, so 115 200 bauds, so 115,200 bauds. And once we establish the serial communication, we want to draw on the display whatever data we get from the serial port. And for that we will use the serial read function that will read the byte that was received by Arduino. And actually I will copy the whole block of the code into our Arduino sketch into the main loop, but I will only keep some of the code like so. So if there is any serial data available, I want to read the byte using the serial read function, and I want to send this byte to the display. And I've already showed you how to send the data to the display. We can use the LCD write data function. So I use the LCD write data function, and I will send the data that I will first read using the serial read function, but we are still missing a few things. The obvious one is not drawing the image inside the loop because we don't need it anymore. But if I look at the draw the image function, or pretty much any function that we've created, draw custom image or LCD clear function, we are first setting the CS pin, the chip select pin, to low state. And that's because you can have multiple SPI devices connected to the same Arduino board, and they will pretty much share all the same pins. They will share the same clock, same data pin, of course same ground and same 5V pins. The only difference there will be is that every SPI device will have a separate CS pin, the chip select pin, and by setting one of those chip select pins to low, you will control to which SPI device you want to currently speak to. Now we only have one SPI device, this display, so what I'm thinking is that we can set this chip select pin to low and keep it low all the time, not setting it to high at any time. So just copy this chip select to low into the setup function. So once we establish the communication, I will set the chip select pin to low, meaning that I will tell the SPI device I want to tell the display that I will send some data. And then same as before, we want to set the correct area to where we will be sending the data. And for that I will use this address set function. Again, copy it and paste it on the end of the setup function. And then once this setup function is over, it will jump to the main loop. And here it will listen for the serial data. And if there is some serial data, it will send it to the display. So let's upload it to the Arduino UNO, and once it's uploaded, let's open the serial monitor. Make sure to set the same speed as inside our serial begin function, which is 115,200 bauds. And here we can send some data to the display, but we are not sending bytes, we are using ASCII characters. So let's see what's going on. Let's say I, for example, send the letter O, which is the hexadecimal of 6F, so 6F, and I need to send 2 bytes for each individual pixel. So let's just say I send the letter O 2 times, so 6F, 6F, which means that I will send the data being 0110, 1111, 0110, 1111, which doesn't make much sense, but we can say that the first 5 bytes are for the red channel, the next 6 bytes for the green channel, and the last 5 bytes are for the blue channel. Or we can just as well open our 5x5 RGB color picker and see what color this is. So 28527 decimal is the 6F hexadecimal, and that should give us some green color. So let's jump back to the Arduino IDE and send the letter O, and as I do so, nothing happens. And there is a good reason for that. We are most likely receiving the data and we are most likely sending it to the display, but we are now updating the top left portion of the screen, which is simply not there. So what I need to do is to send much more O characters, and what I mean by that is much more. So at some point we should hopefully start seeing some green pixels, which seems to be the case. There are a few green pixels on top. So if I keep sending those O characters, I'm slowly filling the screen with green pixels, which means that our approach works. So instead of sending the green pixels, let's just send our image from Photopea. To prevent any gray pixels around the edge of the display, I will create a new fill layer in the black color, so everything is black, and then I will save it as a bitmap file, so export as the BMP file format. Well, let's give it some meaningful name and save it. And use that image to LCD utility to convert it, but this time the size is 240 by 198 pixels. And I don't want to create a C-style array, I want to create the binary file. Let's see how it looks like, and it looks fine. So I will save it. And then I want to send that binary file to the Arduino. I'm not quite sure if that's possible with the Arduino IDE, so I will use a different application called the real terminal. Set the speed to be 115,200 bytes. The port in my case is port number 14, and then I will click the open button, and there is some kind of error, which is saying that I'm still connected to the Arduino using the serial monitor in the Arduino IDE, so I just closed it in here, and click the open button again, and then go into the send tab, and there is a file that could be selected, so I will open our generated file, and then click the send file button. And what happens is that the real-time application is sending the content of the binary file to the Arduino, and then the Arduino is receiving the data and sending this data to the display. So pixel by pixel, line by line, we are slowly drawing the image on the display. And you can see how fast, actually how slow this is, but we don't care about the speed at this point. Really what I want to do is to see how the image looks on the display. And I think it looks great, so it's time to do this for real. And to do that, we cannot use a full screen image because that wouldn't fit into the Arduino UNO. But I think that we can fit image for each individual digit, for each individual gear, and hopefully also the image for the BMW M logo in the middle. And we can actually find it out quite easily by doing a simple math, simple multiplications. Let's measure the size of one label, and I think that the letter R is the biggest one. So if I select the selection around the letter R, I think that we need around 24 by 28 pixels. So 24 times 28, and we need 2 bytes per pixel. And we have 7 of those labels, so times 7, which means that we need around 9 kilobytes for all those label images. And then we have this M image in the middle, which is quite big. So again, let's just select the selection around this image. And this could be maybe, I don't know, 124 by 44 pixels. So 144 times 48 pixels times 2 bytes per pixel, which is around 13 or actually 14 kilobytes. And if I add those two together, so 9 kilobytes and 14 kilobytes, we would need around 23 kilobytes. And that should be possible on the Arduino UNO because again, we have 32 kilobytes of flash memory. And while some of the memory is of course used for the code, I think that we can squeeze 23 kilobytes of the image data. For the current sketch, we only use around 3 kilobytes of data in the flash memory for now. And 3 plus 23 is still below 32 kilobyte limit. So let's go back into Photopea again and start splitting this image into multiple smaller images. I would like to export all those individual gear labels as separate images. And I would like to also export the M symbol in the middle as one image. But I don't want to export those white lines as images, because I think that I can draw those using the draw rectangle function, which also means that I don't want to have those lines inside the M image. Now as for actually exporting the images, I can rename those layers to have the -e- prefix. And then I can go to File, Export Layers, and click the Export Layers button. And that will generate all the images, but those images have different sizes because the image is always cropped to the size of the label. Plus it has a transparent background and I would like to have the black background instead. So what I will do instead is to just go back and create a new layer in the size of our 24 by 28 pixels. And maybe fill it with some color. Let's say for example, I don't know, maybe a pink color. Click the OK button and then lower the opacity. zoom in a little bit and position it over the label, and then create a copy for every single label, so this will be the size of each individual digit. I will also do the same thing for the M symbol in the middle, so again select the selection around the symbol, create a new layer and fill it with the pink color, like so. Then I will hide all the lines, as well as all those pink layers, and then control click on the thumbnail of the layer to load the selection, to load the size of the layer, select edit copy merged, that will copy everything from all the layers, and then select edit paste. And that will paste this image being sized 24 by 28 pixels. If I hide those two layers, you can see that now this is the image that will be exported. So I will continue like this with all the other layers, control click in the thumbnail and then selecting edit copy merged and edit paste, and so on and so on. I think I've missed one here, so 1, 2, 3, 4, 5, 6, reverse and the M symbol in the middle. Again, if I hide all those black layers, those are the images that will be exported. I just need to name those properly using the -e- and then the image name, so it will be the gear reverse, -e- gear first, and so on and so on. And then I can go to File, Export Layers, make sure that this only layers with the -e- in the name is being checked, and then click the Export Layers button. Unfortunately, the image to LCD doesn't support PNG images, so you can either export those as JPEG images if you want, and of course set the quality all the way to 100%, or you can just export those as PNG images and then convert those into bitmap images using any kind of software. For example, I like to use this Airfun View. And if you go to File, Batch Conversion / Rename, you can just set the output format to bitmap file, add all images, and start the batch. And once we have those, we can just open those images one by one in the Image to LCD application and start generating the C arrays. By the way, I've just noticed that this is saying maximum width and maximum height, so I don't think that you have to change it for every single image in case you don't want to be resized. So save it as a C file. I will use the same name as the image. It will even open this in Notepad, and then I can click this button to jump to the next image in the same folder and do the same thing. If you don't want to open Notepad upon every single export, you can just click this Set button and uncheck this checkbox. So we have all the C files generated. Let's add those into our Arduino sketch. And while you can copy and paste those C files into the Arduino sketch folder, I think I will create a new header file that I will name images.h or maybe gearimages.h, and I will paste the content of those C files in there. I want to place those images inside the program memory, so I will type in prog.mem for every single array. And then I want to include this header file into our main sketch. So on our sketch, I will just type in include of our gearimages.h file, and this has to be inside quotes like this. And then we can start drawing those images. We already know the sizes, but we also need to know the positions. And if I jump back to Photopea, I can select any layer and then select this Move tool and click this Distances checkbox, and that will show me the X position, Y position, as well as the size of the layer. So let me just position this window next to the Arduino IDE like so. And I can start putting in the values. So for the reverse gear, the X is 30, the Y is 53, and the size is 24 by 28 pixels. And the image name, the array name, is in the gearimages.h file, which is this one, gimage gear R. So this is the reverse gear image. And I can continue like this with all the other images. And since this part is quite boring, let me speed it up a little bit for you. Again, I'm just putting the X and Y values for every single image and the array name. And in total, we have 8 different images. The final code looks like this, which means that it's time to upload it to the Arduino UNO. And as expected, we use about 23 kilobytes of the flash memory. On the display, we can see the blue background with our 8 images, 7 images for the gear labels and 1 image for the middle logo, which means that now it's time to draw the connecting lines. And as mentioned previously, I will not draw those using images, but I will try to find some draw rectangle function to do this. And if I look into our code, there is indeed a function called fill rectangle. It takes the X position, the Y position, the width and the height and the color. And if you look at the code, we are doing the very similar thing as we were doing with clearing the entire screen, which means sending 2 bytes of data for every single pixel, but we are setting the address, the area where we will draw those pixels based on the X position, Y position, width and height. That said, in order to draw those rectangles, we need to know those sizes and positions. And we should have those lines in our Photopea file, but those lines are drawn in a way that they are below this M symbol, which means that if I draw a rectangle like this in this size, I will later cover most of the part with this image, and I will be just wasting cycles for drawing this part of the rectangle. So I think that what would make sense is to draw a new set of rectangles that are only taking the space that they need to. I will temporarily hide the distances, but before drawing those rectangles, I think that I will hide this image and actually show that image, because I want to see this area where this line is connecting to the M symbol, and while I cannot draw the rectangle like this being skewed, I think that I can draw a rectangle close to the logo that will still look fine. Now before drawing those rectangles, I might add a color fill layer in some dark gray color and fade it out a little bit using this opacity slider like so, and that will make it obvious which lines I've already drawn and which I haven't. So let's draw those using the rectangle tool, and for the reverse we would need two rectangles, so one rectangle I need to change the color to be white color, and the second rectangle, which might go all the way to the right side, maybe to this position. For the first gear, the second gear, third gear and fourth gear we only need one rectangle, and then we need two rectangles for the gear number 5 and 6. But I will not draw the rectangle from top all the way to the bottom, but instead draw it like this, only going to the half of the size, and then this connecting rectangle on the left side, and then the connecting rectangle for the gear number 6. And with all those rectangles created, I think that you know what is the next step, and that is to select the Move tool, click the Distances checkbox, and then select one by one. Make sure that we see both the Arduino IDE and the Photopea window, and then I will be using this Fill Rectangle function. So down inside our code, for drawing the images, I will also draw a rectangle, so fill rectangle, and for the reverse, the X is 40, Y is 85, 4 and 37, and the color is white, which is either FFFF in the hexadecimal or 65535 in the decimal value. I'll probably go with the hexadecimal value, so this is the color, and then I need to do the same thing for each individual rectangle, so let me speed it up a little bit for you. Again, the gears number 5 and 6 both have two rectangles, even when the middle one could be shared, but I will tell you why I am not doing it in a minute. Now, since we draw this line over our M image, we want to first draw that image, so BMW M logo first, and then all the rectangles and gear images. And before uploading it to the Arduino, let's finally clear the screen with the black color, which if I open the color picker, is just the 0 in both the decimal and the hexadecimal value. So LCD clear with the black background color, and then we can upload it to the Arduino. And finally, after 40 or so minutes, we can see the H shifter parent image being displayed on the display, driven only by the Arduino UNO. But this is not the end yet, because eventually I would like to put it inside the car and show the current gear in a different color. Now we can export a new set of images from Photopea in a different color, and I think that we might be able to fit it, because I think that at this point we are using about 23 kilobytes of flash memory, so the images took about 9 kilobytes. We might be able to fit those into the 32 kilobyte limit, but I would rather make it dynamic in a way that I can change the color to be any color that I want. And you've already seen in the beginning of the video that something like this should be possible, because I was switching between a few different color themes. Now having our label images using black and white color is quite nice, because for the black color it means all the bits are set to 0, and for the white color it means all the bits are set to 1. And so what we can do is we can say that if the bit is 1, we want to show a new color, and if the bit is 0, if the color is black, we just want to show the black color. And that's exactly what the bitwise AND operator is for. So there is some example down here. Let me zoom in a little bit. Okay, so let's just say that this first value is our mask image. So this is the image for our labels, which we currently have, having only black and white colors. And let's say that the R value is some kind of color that we want to show. If we have a black color inside our image, so those two zeros are the black color, it doesn't quite matter what are the values in the color, because we will end up with the black color as well. And if we have the white color inside our mask image, we should end up with the new color. So let's try that approach to see if it works. Inside our sketch we have our draw image function. I will copy and paste it one more time and rename it to draw image tinted. And I need to know the color that I want to use, and this color should be made from 2 bytes, and on the Arduino that's the unsigned integer variable. But before I use this color, I need to make a few changes inside our code. Currently we are going over every single byte in the array and then sending this byte to the display, but I want to send the 2 bytes of data at the same time, so I can use the first byte of the color and the second byte of the color. But obviously if I do it like this, I need to go over every single pixel, not over every single byte. So the I variable should only go to width times height and not times 2. So going over every single pixel. And then the index of the byte that we are looking for will be I times 2 for the first one and I times 2 plus 1 for the second one. So far making this change should make no difference in drawing the image. It should still look the same, but now we can use this color. And again, this color is made from 2 bytes. If I, for example, choose the red color, you can see that those bytes are F8 and 00, and we want to apply first byte, so F8 to one of those bytes, and the other one, the 00, to the other byte. And if I scroll up to the LCD clear function, you can see that something like this was happening in here. So there was also this unsigned integer j to set the color of the LCD clear function. And then it was sending the first byte and the second byte, and sending this first byte was done using this bit shift operator. There is actually a more beginner-friendly function in the Arduino. It's called the low byte and high byte, and it does exactly what it says, so it's using either the leftmost byte or rightmost byte. So let's use those functions in our draw image tinted code. So once we get this byte, I will again use the bitwise AND operator, which is the ampersand symbol, so ampersand symbol, and then I will use the height byte function of our color. And for the second byte, I will again use the ampersand symbol, but this time I will use the low byte of the same color. So this function should hopefully draw the image in some color, so let's test it out. Inside our main loop, I will do a quick test by just copying and pasting everything one more time. But this time I will not use the draw image function, but draw image tinted. And let's just say I want to have the R symbol, the reverse gear, in some red color. So select the red color and copy the value of being the F800. And let's actually also use it for those rectangles. And for all the other gears, I will again use the draw image tinted function and show some kind of gray color like it's inside the M logo. So inside the color picker, let's for example choose maybe this color. So let's just copy the hex value of 8430 and use it for both the rectangles and for the images. And once we have it like this, let's try to test it on the Arduino. And indeed we see the reverse gear in the red color and all the other gears in the gray color. Now this solution is not perfect because there are some grayscale pixels in our mask image for the anti-aliased edges, and it's not always playing very nicely with the new color. That said, doing this color tinting in the proper way would take too much CPU cycles, so I guess we have to live with that. At this point, you should have enough knowledge to show any of those gear labels in a different color, so let me talk about a few things that I wanted to talk about but I kind of forgot. First of all, this chip on the PCB is not actually the chip that's driving the display. This chip is responsible for converting the voltage levels between the 3.3 volt and the 5 volt, so you can use the 3.3 volt microcontrollers, for example the ESP32, as well as the 5 volt microcontrollers, for example the Arduino. The chip that is driving the display is on the actual display on the glass, and on this display it's hidden behind this black sticker. Obviously for this display it's hidden behind this glass lens. We have talked about how the Arduino is slow, but we haven't talked about what is the SPI speed. And if I go to the setup function and open the SPI initialization function, we are calling the SPI setClockDivider function and dividing it by 2, which is actually the maximum speed on the Arduino UNO. And since the Arduino UNO is running on 16 MHz, the SPI speed is half of that, being 8 MHz. By the way, in the demo Arduino folder, there were also the software SPI examples. I don't think that there is any good reason to use those, it's just that everything will be much slower. Talking about the speed and the memory usage, when we were using this image to LCD utility and we were sending this test image, there was actually some test image already pre-made, but it was sized 40 by 40 pixels, which means that 40 by 40 by 2 bytes per pixel would take about 3.2 kilobytes, and that wouldn't fit into the Arduino UNO RAM memory, again which is only 2 kilobytes, so that was the reason why I haven't used this one. Also, when we were testing the full screen image on the display, we could have used the Arduino Mega, because the Arduino Mega has 256 kilobytes of flash memory, so our 95 kilobyte image would fit in there, but I thought that using the serial communication with the Arduino UNO might be quite interesting exercise. Finally, if you like shifting, I have found this very interesting keychain for just a few dollars. I will put the link down in the description, as well as a link to the GitHub, where you can find all the files from today's video. As for the next steps, I think that those are quite obvious. I would like to 3D print a custom shifter knob like I've done before. This one is for 7x11 LED matrix display. I just need to make this hole slightly smaller. And I've ordered a few PLA filaments which I cannot wait to try out. This is the PLA Sparkle, which has like small shiny dots inside this black PLA. This PLA metal, as the name suggests, should look like a metal. This is a gray one, the dark gray one. And I also have this one, which is the PLA Galaxy, and that should be changing the color slightly based on the angle. You can see that the base color is like violet, but the highlight goes to green hues. Again, I cannot wait to test all those filaments, and then the next step will be using some smaller Arduino or Arduino compatible board. The Arduino UNO is nice for testing, but it's just huge. You can get the smaller Arduino UNO, it's called the Arduino Mini. It's pretty much the same as the Arduino UNO, except being the half of the size. But I think that this was more meant to be as a collector's item, which you can probably tell by the packaging. That said, you can get the UNO Mini Chinese version, which is almost the same. It doesn't have the packaging or the serial number, but it's much cheaper. You can also get this board, not quite sure if it has a name. On the AliExpress it's called the Arduino Nano Mini Ultra Small whatever, but it's also cheap and it's using the very same chip as the Arduino UNO, and you can see that it is small enough that it might actually fit inside the shifter knob. That said, I might as well use some board with the ESP32 just to have a little bit more memory and performance. We will see. If you have any ideas how to improve this project, please let me know in the comment section. I would like to hear your feedback. If you have any questions, please put those down in the comment section. Thank you very much for watching, and I hope to see you soon. Thanks and bye.